There are two final bits of technology to do with proving equations left to talk about, and I'll talk about both of them in this video. The first of these is what happens if you write from followed by an equation. The second one is another totally new piece of syntax that's sometimes useful. I also want to start showing you that you can freely combine ideas from these last 2 weeks about equations from things from the first 2 weeks. These are not unrelated topics, they're different parts of the same thing. So first I'm going to talk about the second thing that I said, which is a totally new piece of syntax, just like by root in the last video was a totally new piece of syntax. So what we're going to use this for is so that if we know that we're calling a function on equal inputs, then we also know that the outputs will be equal. So I'm going to say, for example, prove fx equals fy. So here I'm calling some function on different inputs, and I want to prove that the outputs are equal. So in order to do this, I can use the new proof rule under f. And if I send under f to ask, then it's going to send me back that I need to prove x equals y. So if you think about it, this makes sense. If you know that x equals y, then you can apply f to both sides of the equation, and then you know that f of x equals f of y. So this says that if you call a function on equal inputs, then it will give you back equal outputs. And this works for any function, so that's why this works even though f is not a function that I've defined. So of course, normally you will do this for a function that you actually have a definition for. So this works also for any number of inputs. So let's say f has 3 inputs and I call them with 2 pairs the same and 1 pair different, and I say under f, it will now just ask me to prove that the middle pair of inputs are equal. On the other hand, if all of these could be different, then ask will generate 3 sub-goals, prove x1 equals x2, y1 equals y2, and z1 equals z2. So it's asking me to prove that each pair of inputs is equal. This is quite useful in quite a lot of situations. Every time you recognize that you are being asked, the ask is asking you to prove an equation where both sides begin with a function call to the same function, then you can use under to make progress. So for example, just to give an example, let's say we have lists, and we have the function snuck, which joins an element onto the end of a list, and I'll just define it quickly. X's from X's. So I can prove, for example, that if x's equals y's, then snuck x is x, snuck x is a, say, equals snuck y is a. So what this says is, if I have 2 lists which I already know are equal, and then I join a onto the end of each of them, then the result is still going to be the same. So here is an example where I'm also using implies like it's weeks 1 and 2. So this is saying that if this equation is true, then this equation is true. So to prove this, just like it's week 1, we know how to prove a implies equation. I'm going to say by imply. And ask will say, given x's equals y's, prove this. And this is a situation where I'm being asked to prove an equation where both sides begin with a function call to the same function. So I can say under snuck to make progress. And actually, ask will accept this now as a complete proof. But there's a missing line here, which is invisible, which is prove x's equals y's. So that's the thing that we would need to do for under, because the second inputs are identical. And this is given because here it is. So that's the complete proof. Okay, so that's under. The other thing that we have to talk about is what happens when you write from followed by an equation. So remember, the general idea of from is that you're saying, tell me everything that I can learn about this thing that I have. So for example, if you want to prove that P and Q implies whatever, by imp I, so now you're given P and Q, and I can say from P and Q, and I'm telling ask, tell me everything that I can learn from the fact that I'm given P and Q. Namely, it tells you that you have P and you have Q. And it's basically also the same when you're programming and you say from a input, you're saying, tell me everything that I can learn about this input. So from an equation is just like that. So if you have an equation as a given, then you can write from of that equation in order to learn everything that you can learn from it. So for example, with lists, let's say that we have two different lists which are both built using cons, and we know that they're equal. So we have head 1 cons tail 1 equals head 2 cons tail 2. So we have, this is saying that this list equals this list. So let's see what we can do if we know this. So let's say we want to prove that this implies whatever by imp I. Now I have this equation as a given, and I can say from this equation. Now, when I send this, what ask tells me is that I know that the heads are equal, and I know that the tails are equal. So ask has taken this equation I had, and it's given me more information that I can learn from it. So you have to think about this for a minute to see that this makes sense. If you have two lists which are equal, and both of them are not empty, then this can only happen if the heads are equal and the tails are equal. Okay, so this trick is also useful with numbers. So let's say I have, if I know that two successors are equal and I want to see what I can do with it. So now I have, given the successor of m equals the successor of n, I can say from this equation, and ask will tell me that I now know that m equals n. So for numbers, this is a way of subtracting 1 from both sides of an equation. So what from an equation does in general is it checks the top constructor of the data on both sides of the equation. And as long as they are the same, then it generates new givens that tell you that all of the parameters are also equal. So that means that this from equation only works when ask is able to figure out that both sides are data, and it can figure out what the first constructor is. So this means that, for example, if I just say prove A equals B implies whatever, so now A and B are things that I don't know anything at all about, I can say from A equals B, and I've learned nothing. Ask just gives me back exactly the same situation. There is not enough information around here for ask to tell me anything that I didn't already know. There is one other situation that can happen, which is that the top constructors on the two sides of the equation are different from each other. And when this happens, then ask knows that something impossible has happened. So this is quite a lot like being false, being given false. So in that situation, ask knows that the universe is broken, and it actually accepts, it forgets what you were doing and accepts your proof as completed immediately. So for example, I can say prove 0 equals 1 implies false. So 0 equals 1 is something that's not true, right? But if I assume it as a hypothesis by putting it on the left-hand side of implies, then I can use this to break the universe. So I can say by imp I. So now I'm given 0 equals 1 and I have to prove false. I can do this from 0 equals 1. And ask accepts this as a complete proof. So what's happening here is that ask looks at this equation and it sees that the top constructor on this side, which is Z, is different from the top constructor on this side, which is successor. So because a 0 equals a successor, ask knows that the universe is broken. And so if the universe is broken, then you can prove anything. So this trick also works for lists as well. So I could say that if you know that the empty list equals head cons tail, so this is also not possible because head cons tail always gives you a list that isn't empty. So here, the top constructor on the left-hand side is the empty constructor. The top constructor on the right-hand side is cons, this one. So I can do the same thing here. So now I can prove false from this equation. Ask will accept this. There we go. Okay, so the big picture with this stuff is that normally most of the time you will still be proving things by induction first, but these are small bits of technique that will come up sometimes for individual steps in a bigger inductive proof. So for example, sometimes we'll be in a situation where we're given some kind of invariant about a data structure, and that might be in the form of an equation. And then, for example, we might want to prove that calling some function on that data structure will preserve the invariant. So then if the equation is true for the inputs, then the same kind of equation is true for the outputs. So this is the sort of things that we're building up to around towards the end of the course.